So today we're going to talk about kind of the weirdest stuff you are going to hear in this class, and it's the topic of quantum numbers. Quantum numbers are essentially addresses for electrons. Just like we discussed before going into this, one will be dependent upon the one before it. There are 4 of them, 4 quantum numbers. 3 of them are connected to one another, and then the last one, the spin quantum number, is independent of these 3. The first one is called the principal quantum number. It's given the symbol n, lowercase n. And what this does is it gives the average distance from the nucleus for the electron. So as n gets larger, the electron is farther away from the nucleus. N can have integer values beginning at 1, going up to 2, 3, 4, up to infinity. If the quantum number n is equal to infinity, that means the electron has been removed from the atom and you've made a cation. Okay, so you kind of need to know that rule right there. Those are the values for n. The next one is called the angular momentum quantum number. It's sometimes called the azimuthal quantum number. Your book doesn't call it that, but a video I'm going to show you does call it the azimuthal quantum number. Don't write that down, just remember you've heard it. Its symbol is a lowercase l. I usually do a script L because it's very difficult to tell a lowercase typed L from a 1. And what the angular momentum quantum number does is it gives the shape of the orbital. Okay, and there are 4, well, there's a bunch of different shapes, so just let me show you those shapes. Okay, we'll discuss the fact that there are differing numbers of them later, but you can have a sphere shape. It can be small, it can be big, but it's shaped like a sphere. You can also have orbitals that are shaped like dumbbells or figure 8s. They can be oriented in different directions. We'll talk about that later. You can also have, and this is a whole set of orbitals down here, that can be shaped like 4-leaf clovers, except for the one that looks like a dumbbell with a donut around it. So this is one set, this is a second set, and this is a third set. But those are the kind of shapes we're talking about when we talk about the L quantum number. Okay, the values for the L quantum number are dependent upon the N quantum number. They start at 0, 1, 2, up to however many, but they go to a maximum of n minus 1. So say if n was equal to 2, if n equals 2, your L values can be 0 or your L value can be 1. You can have either of those values. Now, n and L are used together. And to use n and L together, the L values are replaced with letters. So if the value of L is 0, it is called an s orbital. If the value is 1, it's called a p orbital. If the value is 2, it's called a d orbital. If the value is 3, it's an f orbital. So they're written together in a fashion like this. We might talk about a 1s orbital. The 1 is the n value, and it is n equals 1. The s is the value of L, and when we have an s, it means L is equal to 0. Over here, we could have a 2p orbital. P orbitals are the ones that are shaped like dumbbells. This 2 means n equals 2. It means it's farther from the nucleus. And if you have a p for the second value listed, that means the L value is equal to 1. Anytime the L value is equal to 1, we're talking about p orbitals, the dumbbell-shaped ones. When L is equal to 0, we have s orbitals, which are sphere-shaped. With L equals 2, we have d orbitals, which are the figure 8s, or the one that's a dumbbell with a donut around it. Okay. The next batch or the next quantum number is called the magnetic quantum number. Okay, it is given the symbol m sub L. Again, I used a script L, sub meaning subscript, and it gives the orientation of the orbital in space. So we're talking about a Cartesian axis system, x, y, and z. The values of m sub L are dependent upon the values of L. So m sub L depends on L depends upon N. They're connected. M sub L can go from a value of negative L through 0 to plus L. So if L equals 0, well, negative L would be 0, 0 would be 0, positive L would be 0. The only m sub L value would be 0. If L is equal to 1, m sub L equals negative 1, 0, or positive 1, any of those values. If L equals 2, your m sub L values can be negative 2, negative 1, 0, 1, and 2. Now, how does this work? Okay, if L equals 0, we're talking about an s orbital, which is a sphere. You've got one value for it, which means there's only one orientation. Well, if you look at a sphere, whoops, how many ways can you orient that sphere? Just one. No matter how you twist it or turn it, it's going to look the same on the Cartesian axis system. If you go to L equals 1, those are p orbitals. Those are the ones that are dumbbell shape. There are 3 values when L equals 1, negative 1, 0, and 1. That means there are 3 orientations. Where are we? 3 orientations. So here we have the p orbitals, and you have one that's aligned along the z-axis, one on the x, one on the y. 3 orbitals pointing in 3 different directions on a 3-dimensional Cartesian axis system. If L is equal to 2, we're talking about d orbitals. If L equals 2, you have 5 values. They are negative 2, negative 1, 0, 1, and 2. That means you have 5 orientations. Lo and behold, these are the d orbitals. 1, 2, 3, 4, 5 orientations. These illustrations are in your book. The last one is the spin quantum number. It is given the designation m sub s, and it has 2 values. M sub s can either equal a positive 1/2 or a negative 1/2. What that means is the electron can spin in 2 different directions, clockwise or counterclockwise. The m sub s quantum number is not connected to the other 3 at all. It is totally independent. And what it does, we'll discuss this later, but it allows 2 electrons in a single orbital. And that's it for quantum numbers.